Alright everyone, and welcome back to the AI Research Roundup. I am your host, Alex. Today, we're diving into a new paper called Unifying Appearance Codes and Bilateral Grids for Driving Scene Gaussian Splatting. This work tackles a really common problem in creating 3D scenes from photos, especially for autonomous driving. The issue is what's called photometric consistency, which is just making sure the lighting and colors look the same across different images. When they don't, it can mess up the 3D reconstruction. This paper introduces a new method, a multi-scale bilateral grid that improves 3D scene accuracy, which is vital for a car to correctly identify obstacles. And if you want to dive deeper, the authors have released a really comprehensive repository. It has the official code for this work, of course, but also everything you need to get going, like instructions for training and evaluation, plus links to all the pre-processed data and pre-trained models. This is all built around the core technique of Gaussian splatting, which is a method for creating 3D scenes by rendering millions of tiny, colorful orbs called Gaussians, making the whole process very fast and realistic. Okay, so this first figure really visualizes the core problem and the proposed solution. It compares three different methods. Row A shows the standard appearance code method. It applies a single global affine transformation, which is basically one color and brightness adjustment for the entire image. You can see it struggles with details and creates blurry artifacts. Row B shows a bilateral grid, which is more powerful because it can make adjustments pixel by pixel. The result is better, but the paper notes these are hard to optimize. Finally, row C shows this paper's new multi-scale approach, which is much sharper. And on the far right, we see the geometric accuracy measured by something called chamfer distance, or CD. Chamfer distance is a score for 3D accuracy, where a lower number is better, and the new method clearly achieves the lowest score. Alright, so this diagram gives us a great overview of how their multi-scale method actually works. The process starts with the input photos, which are used to build a 3D representation called a Gaussian scene graph. From this graph, the system generates an initial rendered image. The key innovation is the multi-scale bilateral grid, which has 3 levels of detail. A guidance map, based on the rendered image's brightness, helps slice out the right color corrections from each grid level, from coarse to intermediate to fine. These corrections are then fused together to process the final image. So building on that architecture, this next figure shows us some direct comparisons, both at night and during the day. Again, we see the 3 methods compared. In the red boxes, you can see how the proposed method in row C renders the streetlights much more cleanly at night and produces a sharper moving car during the day. What's really key here are the geometric error maps on the sides. Here, yellow indicates a high LiDAR error, while purple means low error. Our method clearly shows more purple, which matches its much lower chamfer distance score. And this figure gives us an even more detailed look at how the method handles a whole range of really tough, real-world conditions. For instance, in section A, look at the specular highlights, those bright reflections on the car. The baseline blurs them out, while the proposed method keeps them crisp. It's a similar story for motion blur and for the incomplete geometry in section C, where the baseline turns a fire hydrant into a blurry ghost. The new approach also cleans up duplication artifacts in the sky, and, as seen in the last row, performs much better in low light. So to sum things up, the key takeaway here is how this paper unifies appearance codes with a multi-scale bilateral grid. This novel combination is what allows the model to handle those really tricky visual effects we saw, like bright highlights and motion blur, far better than previous methods. This work is a significant step forward for creating photorealistic driving simulations, which are crucial for training and testing self-driving systems safely. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.